Greetings everyone, welcome back into Calculus 2. It's time to finish up our basic skills on testing for convergence. There's 2 tests left. The first, the ratio test. Probably the test that I hear from a lot of my students that they like the best, and I think it's probably just because it requires the least amount of effort for the most amount of gain. It also hits a lot of the really popular types of series that are going to come up when we start doing things with the functions and what we call power series coming up next. So ratio test is pretty popular. It's also a little bit different than some of the other tests that we've done so far in that not only is it a test for any kind of series, but it tests for absolute convergence. Just like the next test that we're going to talk about in this lecture, the root test, it also checks for absolute convergence. Okay, so that is sort of a good thing about this test, but of course, if you're running into a series that's conditionally convergent, well then it will probably come up to fail the test. Not necessarily show divergence, just fail the test where you need another one. Okay, so here's the basics of the ratio test. If you have some series, okay, A equals the sum of the sequence A sub n, little a n. Then if I take the limit as n goes to infinity of A sub n plus 1 divided by A sub n. Now let's think about this for a second. Remember, a lot of our stuff where we determine convergence or divergence has to do with whether or not your sequence is decreasing. So right here, if I have A sub n plus 1, that's like saying the next term. And then A sub n, that's the current term. Okay? If I do the next term over the current term, that's like comparing the sizes with a fraction, with a ratio. A lot like we did with the limit comparison test. We were comparing two different sequences by making a ratio. Well, it's the same idea here, except all I'm comparing are 2 terms of the sequence that come one right after the other. Okay? Now remember, we want our sequences to decrease. So if the next term is smaller than the current term, then this fraction should come out to be less than 1. The absolute value is so that we can show absolute convergence, and so that we can basically ignore a lot of the alternating series parts. Okay? So if I say that this limit is L, right, then if L is anywhere between 0 and 1, but notice not equal to 1, not equal to 1, okay, then your series A absolutely converges. That's a pretty nice thing. I'm just going to throw down one limit with the 2 pieces in it. Sure. It just has to be less than 1 in size. And of course, it's not going to be negative. I didn't actually have to put the 0 on the other end there because the absolute value here, okay? But to be clear, I will get some sort of decimal fraction, whatever, in between 0 and 1. Then your series is absolutely convergent. If L is greater than 1, strictly, no equals. If it's something bigger than 1, then your series diverges. And if L is 1, then the test failed. It doesn't mean that it diverges. It doesn't mean that it converges. It means this was not the right test for you to choose if it's equal to 1. Okay? Big misconception, big thing that gets mixed up here. Don't get this test mixed up with the limit comparison test. Okay? The limit comparison test is any number but not 0 and not infinity. This one is anything between 0 up to 1 but not 1, okay, is convergent. And then greater than 1 is divergent. Don't get those 2 series mixed up, because I know they both use ratios to do their work here, and they both use limits to do the same thing as well. Okay? So this is basically the idea of what you want from the ratio test. So what you're going to be looking for from this test is things that depend a lot on multiplication, since we'll be doing a lot of ratios with these kind of things. You may find that certain categories don't work well with this test, which is why we have the other tests. Okay, this is a really nice test, and it is one that gets used a lot. However, the reason we have all of the different tests is because not everything's going to work here. So I have a few quick examples before we do the more advanced examples to show you the difference here. Okay, so I've got a series that diverges, right? We could do that with comparison test. We have a series here that's conditionally convergent. You've already seen that from the alternating series lecture. And then we have something that's convergent. You've already seen that one from the comparison lecture, and we also talked about it in one of the other ones as well. Okay, so we already know the fate of these, but let's use the ratio test so that you can get a feel for these. With the ratio test, all I'm going to do is set up this limit. That's it. That's what I have to do. I'm going to take the sequence n over n squared plus 4, and I'm going to set it up. So I'm going to say, what's the limit as n goes to infinity of the absolute value of n plus 1 over n plus 1 squared plus 4 divided by n over n squared plus 4. Okay? Now, the way we had this one already in a fraction, notice it was easier to set up this ratio as a horizontal division. Because then what I'm going to do is I'm going to flip and multiply. So I've got limit as n goes to infinity, n plus 1. Yeah, and you'll notice I dropped off the absolute value signs. That's because everything here is positive. In other circumstances, you'll find that I end up keeping them. It just depends on the type of thing that we're dealing with. Here I've got all positive terms. Okay, so then it's times n plus 1 times n squared plus 4, and then the n plus 1 squared times n, like so. Okay, now take a look at this limit. I'm just going to hit the most important pieces. Notice right here, if I were to multiply this out, the n plus 1 times the n squared plus 4, then I'm going to have n to the third, right, plus, and then I'll have n squared, I'll have 4n, I'll have 4, plus some other garbage that's lower than n cubed. Okay, you'll see what I mean in just a second, why that's the only one that's important. In the denominator, I have n plus 1 squared, which is n squared plus 2n plus 1 plus 4 times n. All right, all I did was multiply out the n plus 1 times n plus 1 there. And then I'm going to be doing n times n squared, which means I'm going to have an n cubed plus and then a bunch of other lesser things. So you'll notice that what I'm really focusing on is the highest power in the numerator and denominator here. And they happen to tie. And as n goes to infinity, remember the technique is to look at the coefficients, 1 and 1. So this limit equals 1. Well, ratio test, if the limit equals 1, then it's inconclusive. No answer. What does that mean? Try a different test. I don't know if it converges or diverges yet. Okay? We already know that we can do a limit comparison test on this one. Pay closer attention to the type here. This is one of those ones that works really quickly, really well with a p-series. If I just compare this one to 1 over n, I could very easily make it work in a limit comparison test. So not so good for the ratio test, works really well with the limit comparison test. All right, what about this one? Well, alternating series was a really good test for this one. Let's see what happens with the ratio test. The ratio test, I will take the limit, right? Let me get my marker here. The limit as n goes to infinity of the absolute value of negative 1 to the n plus 1 over n plus 1 divided by n over negative 1 to the n. Since I'm doing absolute values here, though, with my multiplications and divisions, basically all these negative 1s are just going to go away. And that's going to leave me with the limit as n goes to infinity of n over n plus 1, which same result as earlier. These two are tied powers. I can put infinity into both, and I'm going to get 1, which is no answer. Okay, so then I would go on to say, oh, wait, it's an alternating series. Let me try it in alternating series. Okay, that happens to be a conditionally convergent series. Okay, but I got no answer from this one. I happen to know that this one is also divergent, right? Because I can compare it to 1 over n. But again, we got no answer. So I'm just showing you how there really is a specific type that works the best with these. Okay, now think back or go ahead and rewind, go back to one of the last video where we talked about the ones with the factorials. And you remember every now and then especially when we hit these factorials, we kind of hit a bit of a bump, and it's like, I can't really turn factorials into the real things, into a real variable to do any of the integral tests, and I can't use p-series with the factorials. I really can only do very limited comparisons to try and do those. Some limit comparisons would work out okay, but we had to do direct comparison mostly with these, right? So this is where the ratio test is going to start shining for us. Factorials and exponentials and things like the geometric series and different things like that. This test and the root test that we're going to talk about in a minute are perfect for these. Okay, so this is like our kryptonite, our good weapon against these factorials. Watch what happens when I apply the ratio test to this factorial. I'm going to take the limit as n goes to infinity, absolute value, 1 over n plus 1 factorial divided by 1 over n factorial. Okay, so again, I'm going to multiply by the reciprocal there, which is going to give me limit as n goes to infinity of n factorial over n plus 1 factorial. Okay, so then this is great because those are both based off of the same value pretty much. This is just one more than this one in the factorial run. So what I have is the limit as n goes to infinity of n minus 1, n minus 2, all the way down to 2 times 1. And in this one right here, I've got n plus 1 times n minus 1 times n minus 2 down to 2 times 1. Notice they match with the n's, they match with the n minus 1s, n minus 2, all the way down. And the only thing left is n minus 1 in the denominator. So then my limit as n goes to infinity is of 1 over n plus 1. And this, as n goes to infinity, makes the denominator extremely large, which makes the limit go to 0. And 0 is less than 1, right here. Therefore, this series converges absolutely. Okay? So this is what the ratio test is really going to be the best at if you have these kinds of structures. And that doesn't mean it's the only kind. You can try this on any one of them. Okay? You just have to look out for these certain kinds. It doesn't work as well for things that can be easily compared to p-series and things that are already pretty quick to get through the alternating series test like that. Okay? Really awesome with things with exponentials and factorials. So let's go take a look at some more examples. So let's do some more examples using the ratio test. Sum from n equals 0 to infinity of n factorial over 5 to the n. Seems like a perfect setup for a ratio test. It's got a factorial and it's got an exponential, right? So I'm going to set up my limit as n goes to infinity of the n plus 1 term, which is n plus 1 factorial over 5 to the n plus 1 divided by n factorial over 5 to the n. So the lovely thing here is that when I do the reciprocal and multiply, I'll mix and match the things that go together. So when I do this, I'll have the limit as n goes to infinity of n plus 1 factorial over n factorial times 5 to the n divided by 5 to the n plus 1. So it's right here that you need to see just the intricate little ways that we can split this up. The n plus 1 factorial here is the same thing as n plus 1 times n factorial. So the n factorials will reduce here. And then over here I've got 5 to the n and 5 to the n plus 1. Don't forget that 5 to the n plus 1 is really just 5 to the n times 5 to the 1. So the 5 to the n's will reduce here. And what that's going to leave me with is the limit as n goes to infinity of n plus 1 over 5. And since there's an n in the numerator and none in the denominator, this is going to go to infinity. Infinity is greater than 1, therefore you can say that this diverges by ratio test. All right, next, n equals 0 to infinity here, and I have n times 2 to the n over 3 to the n plus 1. So if this were, something else in, like we were doing a different test, you would probably lean more towards a limit comparison where this kind of looks like a geometric there, right? I have 2 over 3 all to the n. But the other problem is the times n. So it has that multiplication mixture going on here. That makes it kind of a perfect candidate for ratio test also, because I'm going to be able to split, divide and conquer for a better, lack of a better way of saying it, right? So look, I'm going to set up the limit here. The limit as n goes to infinity of the absolute value n plus 1 times 2 to the n plus 1 over 3 to the n plus 1 plus 1 divided by, so times, I'll just go ahead and do the multiplication by the reciprocal here. Just remember I'm dividing by this. Okay, so times, that's going to be 3 to the n plus 1 over n times 2 to the n, and my absolute value there. So then let's mix and match here. That means that I've got the limit as n goes to infinity of n plus 1 over n, right? That's these two pieces that are multiplied and divided. I have times 2 to the n plus 1 over 2 to the n. That's these two pieces. And then I'll also have times 3 to the n plus 1 over 3 to the n plus 1 plus 1. Let me write that a little bit better. Plus 1. Okay? So this one, the limit is n goes to infinity. This limit right here, we know that goes to 1. Right here, don't forget that 2 to the n plus 1 is the same thing as 2 to the n times 2 to the 1. So then this limit right here, since the 2 to the n's are going to wipe, is going to leave me with a 2. And then next on this one right here, what I'm going to do is I'm going to rewrite this piece of the limit right here. What I'm going to do is I'm going to divide everything by 3 to the n. Okay? So divide by 3 to the n, divide by 3 to the n. Okay? So what that becomes is 1 plus 1 over 3 to the n over, now this is 3 to the n plus 1. If you divide by 3 to the n, you'll just be left with the 3 to the 1 portion. So 3 plus 1 over 3 to the n. N is going to infinity. So these pieces are going to go to 0, reduce to 0. And I'm left with the 1/3 there. Okay? So therefore, this piece of the limit right here gives me 1/3. So I have 1 times 2 times 1/3. The overall limit is 2/3. Since 2/3 is less than 1, then I say that this converges. Absolutely. Okay? Converges absolutely. Now let's see this one. N squared times e to the negative n. It might be easier for you to look at it another way. Well, actually, you know what? Let's go ahead and do it this way, because I want to write it the way the thing says in the original rules. So I'm going to set up my limit here. This is going to be the limit as n goes to infinity of the absolute value of n plus 1 squared e to the negative n plus 1 divided by n squared e to the negative n. So that's the n plus 1 term on top, and then that's the normal n term right there that we've been dealing with. So then this is going to be equal to the limit as n goes to infinity. And I'm just going to split this up right here. I've got the n plus 1 squared over n squared. But we already know what happens to that piece. I have an n squared over an n squared. The limit of that one is going to 1. Times, I have e to the negative n minus 1, and then over e to the negative n. Okay? So right here what I've got is, instead of e to the negative n minus 1, what I really want to say is that this is going to be the limit as n goes to infinity of e to the negative n times e to the negative 1 over e to the negative n. The e to the negative n's are going to reduce, and it leaves me with the e to the negative 1 power. So this equals e to the negative 1, which is just 1 over e, like so. And 1 over e is less than 1. I know that because e is greater than 1. E is 2.718. So it's almost 1 over 3. It's a little bit different than that, but close. And since this is less than 1, I can say that this series converges absolutely. All right. Next, I have n factorial to the third over 4n quantity factorial. This one would be a nightmare with most other forms of the convergence testing, because not only does it have factorials, but it has a factorial in an exponent, which means you'd really want to write out n factorial, n factorial, n factorial, and then the 4 times n factorial. Remember, that does not mean 4 n factorials. It does not mean that. Okay? That means that you take whatever n is, multiply it by 4, and you have that much longer of a factorial. Okay? So imagine n factorial, right, all the way up, and then n plus 1 up to whatever 4 times n is, that much more. That's what 4n factorial is. So the ratio test is one of the best tests for this particular setup. Okay, let's go ahead and set up that limit. I've got the limit as n goes to infinity of absolute value n plus 1 factorial cubed over 4 times n plus 1 factorial. Be careful with your parentheses there. That was why I left the parentheses off. The cube is still on this whole thing there, though, okay? So then times, I'm going to go ahead and do the times because I'm going to do the reciprocal. This is actually dividing. I'm just taking one step extra here. So it's going to be 4n factorial and then n factorial cubed. Absolute value like that. Okay, so that's my initial setup here. I'm going to regroup some things. So that's going to be equal to limit as n goes to infinity. And just to make this a little bit simpler, what I'm going to do is I'm going to take these cubes here and I'm going to pull it kind of out like this. This is going to be one big thing cubed. And what I've got is n plus 1 factorial over n factorial. Right? But we've already talked about that. N plus 1 factorial over n factorial just gives me n plus 1. Okay? So this right here is going to give me n plus 1 cubed. Okay? That's what this piece is going to give me. We'll write it out in the next step. Times, I've got 4n quantity factorial over 4n plus 4 factorial. Now think about that for a second. What I did was, it was 4 times n plus 1, the next term. But really I'm just going to distribute there. So it's 4n plus 4. And so what I'm going to get is I'm going to rewrite this 4n plus 4 factorial so that I can reduce it with the 4n factorial. It's got to count down to do that. 4n plus 4 factorial is the same thing as 4n plus 4 times 4n plus 3 times 4n plus 2 times 4n plus 1 times 4n, and then it's going to keep going factorial. So notice I can wipe out the 4n factorial with this 4n factorial, but I still have the 4 terms that were higher than 4n. Okay? And then this is going to reduce to just give me n plus 1 cubed. So now let's see what we've got here. This limit is going to equal limit as n goes to infinity of n plus 1 cubed over, I've got 4n plus 4, 4n plus 3, 4n plus 2, 4n plus 1. That's where I'm at now with this limit. Okay? Well, we're pretty much done. Notice my numerator is going to be on the order of n to the 3rd power, right? That numerator right here, I've got n to the 3rd power. Look at the denominator. If I multiply this out, this is going to be around n to the 4th, right? Since the denominator has the bigger power and this is going to infinity, this limit goes to 0. Therefore, this series converges absolutely. Okay, this one should look a little familiar to you from the last one. We just didn't have the 4 to the 2n plus 1 in it. This is what it would look like if you were trying to use a series to approximate the sine of 4 radians, right? So we would hope that this would actually converge, right? And hopefully it would converge absolutely, right? Because of the way this works. Okay, so let's use the ratio test. I'm going to set up a ratio test here. So with the ratio test, I'll have the limit as n goes to infinity of the absolute value. Now, we're doing the absolute value, right? So what's going to happen to the -1 pieces? They're basically going to get wiped out. So I'll go ahead and assume that step. I'm going to have 4 to the 2 times n plus 1 plus 1 over 2 times n plus 1 plus 1 factorial. Divided by a fraction, so I'm going to flip and multiply here. 2n plus 1 factorial over 4 to the 2n plus 1. Alrighty. So then this gives me the limit as n goes to infinity. Okay, now let's simplify these. If I distribute the 2 in here, that's going to be 2n plus 2, but then plus 1 more is going to make it 4 to the 2n plus 3. In the denominator, I have 4 to the 2n plus 1. Okay, so I'll be doing that piece independent. And then I've got 2n plus 1 factorial over 2n plus 3 factorial. Right? Okay, so let's reduce some here. I have 4 to the 2n here and 4 to the 2n here. So those are going to reduce once you split it up. It'll be 4 to the 2n and 4 to the 2n. But I still have 4 to the 3rd power and 4 to the 1 power. Okay? So this is 4 to the 3 divided by 4 to the 1, which is going to give me 4 squared. Right? That's what it's going to give me from that piece. Now here, on this factorial, remember this is the higher one. This is plus 3. This is plus 1. So I've got to count down. All right? That's how we handle these factorials. I count down until I find one that matches. So from 2n plus 3, 2n plus 3 times 2n plus 2 times 2n plus 1. Now it matches, so I just say factorial to finish out the rest. And then those pieces will reduce. Okay? So my limit, what's left over, I have the limit as n goes to infinity of just 16 because of the 4 squared, right? That's going to be left on top. And then in the bottom, I've got 2n plus 3 times 2n plus 2. There's no n's in the numerator, and there's n squared in the denominator. That limit is going to 0. 0 is less than 1. Therefore, this one converges absolutely. Okay? So I know we have a lot of them that converge. You'll see that it's just in the arrangement of the way these things are, right? And it's a very delicate balance the way these things are. If I didn't have the 4 on the n factorial here, right, that wouldn't have converged. This one diverged because the factorial in this case, is more powerful than the exponential piece. You kind of expected this one to converge because of the way the geometric piece is here. Although the n may have thrown a monkey wrench in it there, you got to watch out. And then and then this one right here, I mean, the exponential is way more powerful than the polynomial. So you can probably take a guess on this one. If this one's kind of like this one, I've got an exponential in the denominator, which is way more powerful than the polynomial up top. Okay, so you can guess this one probably converges as well. Okay, let's set up a limit and find out. So I'm going to be doing the limit here as n goes to infinity of the plus 1 term. So that's n plus 1 cubed minus 2 divided by 3 to the 2 times n plus 1. And of course that's divided, so times the reciprocal, I'll have 3 to the 2n over n cubed minus 2. All right, so at this point you'll want to regroup like we've been doing. I'll have the limit as n goes to infinity of n plus 1 cubed minus 2 over n cubed minus 2. Okay, so think about the way these limits work. I've got n cubed as my highest power here and also n cubed here. Okay, so these, the coefficients are going to be your determination, right? That's going to go to 1. Times, I've got 3 to the 2n on top divided by, I've got 3 to the 2n plus 2. Okay, so just like before, I'm going to have a 3 to the 2n in both places. That's going to leave me with a 3 squared in the denominator. No n's. So this piece right here goes to 1/9. Therefore, the overall limit is 1 times 1/9, which is 1/9, which is less than 1. Therefore, this one also converges absolutely. So I hope you see now just how useful the ratio test is, especially when you're dealing with exponentials and factorials, which come up quite often in a lot of the series that we deal with. Next, let's talk about the root test for convergence. It's very similar in structure to the ratio test, except I only need the a sub n. But it ends up being the same caliber as the ratio test. And if you know some of the proper tools to put with it, it can be just as quick, sometimes quicker, and easier to simplify. It just depends on the problem. But it's going to be very good for things that are exponential, for things that are factorial, just like the ratio test. So here's the idea. If we have a series, right, like we've been talking about, then I need to take the limit as n goes to infinity of the nth root, not square root, not third root, not fourth root, nth root. So in other words, the root keeps getting stronger as n gets larger. Okay? So a sub n, if this thing converges, a sub n should be shrinking. And then as n gets larger, the nth root should be shrinking it even more. It should be chopping it up. Okay? So if I let this limit be L, okay, then it actually has the same rules as the ratio test. That limit L is less than 1 in size, then the series is going to converge absolutely. If L is greater than 1, then the series is going to diverge. And if L is equal to 1, it's inconclusive. Same rules as a ratio test. Don't get those rules mixed up with the limit comparison test, right? I already warned you about that. And second warning on that one. Okay, now A lot of times this one gets passed up because everybody gets a little daunted by that nth root. Well, I stumbled across an article that also made me realize that that was one of the reasons I might want to try doing this test more often as well. And it's something called n factorial and the root test by Charles Mumma. You can Google that and read it. It's a really short article with some really poignant pieces on how to quickly use the root test for some very potent results when it comes to infinite series. Okay, so I've written down some useful limits that you can use to help you simplify a lot of these things that would probably involve an nth root. Okay, so the limit as n goes to infinity of the nth root of some constant. And by the way, most of these can be shown just by changing the nth root into the 1 over n power, and then doing the little logarithm trick where you take a logarithm of both sides, and then you can drop the power, and it turns into some sort of L'Hopital's rule a lot of times. So all of these can be shown in that same light. Okay, but anyway, if you take the nth root of a constant, then that's going to go to 1. Okay, something a little bit more potent. If we take the limit as n goes to infinity of the nth root of n to some power k, okay, that's also going to go to 1. Then if you take the limit as n goes to infinity of some polynomial, look, it's like I'm taking these two first limits and piling them on top of each other, okay? Now, of course, there's going to be big exceptions for, if you try to trip this thing up. But if you've got normal, nice powers, and this is just a polynomial with some n squareds and n cubes and things like that, then the limit is still going to come out to be 1. That's how powerful that nth root is compared to something of a finite power size, right? N to the k could be a large power like n to the 100, but that doesn't matter because eventually this root is going to pass it up while going to infinity, the infinite root, right? It's going to eventually overtake that big time. So for all of the polynomials that we would ever run into, that limit's going to be 1. Here's an interesting one, though. The nth root of n factorial. And then that one's going to go to infinity. The n factorial is more powerful than the nth root in this case. Right? So that one's going to go to infinity. However, if you take the nth root of n factorial and divide it by n, you actually get a finite answer of 1 over e. And this is a huge result from Mumma's paper right here. This guy is a very interesting limit to have in your answer there. Okay, and then also I investigated a little bit further. If you let the n's power in the denominator go higher than 1, so if it was n squared or n cubed or n to the 4th power, then this limit starts going to 0 instead, right? Right here, they're kind of balanced, and you get a finite number. And then right here, if you let the power on the n increase in the denominator there, it starts to overtake it. Okay, and so the limits would go to 0. These limits can be useful tools while using this particular test of series. Okay, so let's do a couple of examples here. I know we already know this one converges, but I want you to see how this can easily take care of this one. For this one right here, I'll just take the limit as n goes to infinity of the nth root of 1 over n factorial. Okay, so since I can split this, I basically have the limit as n goes to infinity of 1 over the nth root of n factorial. And as we just saw, the limit as n goes to infinity of the nth root of n factorial is infinity. So it's going to be 1 over infinity, which is going to go to 0. And since 0 is less than 1, right, we're in this category right here, this one converges absolutely, as we've already seen previously, right? Just another way to prove the same thing. Next, Let's look at the one where the ratio test failed. And I'm going to show you the root test is about the same caliber here. That means I'm going to take the limit as n goes to infinity of the nth root of n over n squared plus 4. And again, I can split that root because it's just division. So I'll have the nth root of n and the nth root of n squared plus 4. Okay? Now both of these limits right here come off of these guys right here. If I have the nth root of n to some power, which n to the 1, right? Then that's going to be 1. If I have the nth root of some simple setup polynomial, that's also going to be 1. I'm getting an overall limit of 1 here. And again, if it's equal to 1, then I get an inconclusive, no answer, right? And all that means is that you have to try a different test. In this case, limit comparison would be great for this particular series. Now, I kind of glossed over this real quick, but don't forget, this has an absolute value on the inside of that root. And that's because you don't want to be taking any even roots of negative numbers. Well, that's one reason, but also we're proving absolute convergence as well. Okay? So if anything's alternating, anything has the negatives, you're going to be taking the absolute value. But I had nothing but positive values on these, which is why I didn't have the absolute value there. Okay? But technically it was there. Let's get a few more examples of root test. So let's finish up our video with 6 good examples of the root test. And you can see that it's very similar in results to the ratio test. So I have the series from 0 to infinity of negative 1 to the n, 2n factorial over 8 to the 2n plus 1. To do the root test, I'm going to take the absolute value of this, which means the negative 1 is going to get dropped off. So I'll have the limit as n goes to infinity of the nth root of 2n quantity factorial over 8 to the 2n plus 1. Okay? So some manipulations here. I'm going to split the radical top and bottom, right? I'm going to do the numerator and denominator separately. And then also the 8 to the 2n, and then I'll have 8 to the 1 that I'm going to separate through multiplication. So I've got limit as n goes to infinity of the nth root of 2n factorial over, this is going to be the nth root of 8 to the 2n times nth root of 8. Now the nice thing about the nth root of 8 to the 2n is that the nth root and the nth power are going to wipe out, leaving me with just the 8 squared there. Okay? So this piece right here is just 64 because the nth power and the nth root. And as you can remember from our other limits, the nth root on a constant, this piece is just going to be 1. And then the numerator is what really hits. Remember, the limit as n goes to infinity of the nth root of n factorial is infinity. 2n is bigger than n. Okay, so direct comparison, this limit is going to infinity in the numerator. Therefore, I'm getting infinity for the overall result, which means that this series diverges. Because naturally, infinity is larger than 1. Okay, next, I have a geometric series, right? We already know this converges. Watch what happens when I use the root test to prove it too. If I take the limit as n goes to infinity of the nth root of 9/13 to the n power. It's already positive, so I don't need the absolute value. Nth root n power, the only thing left is the 9/13. I get 9/13 as the answer, which as we know is less than 1. Therefore, we can say converges. Absolutely. I know geometric series is an even quicker investigation. You can say 9/13 is less than 1, and then by geometric, and then also with the geometric you can give me the actual result. But just to show you, things with the powers like that work really well with the root test. Okay, this one right here. Another example of something with that n power that will work really well with this root test. If I take the limit as n goes to infinity of the nth root, I'm going to end up with the nth root of the numerator and the nth root of the denominator. According to our limits on the nth root of polynomial pieces, that's going to be 1. And then the nth root with the n power here is going to leave me with 3 squared, which is 9. So I'm getting 1/9 here, which is less than 1. So we can see converges absolutely. Okay. Next, let's take a look at this guy. Now, some of these series, as you're going to see, without the root test, it would be a real headache, even with the ratio test, because the n power is on an entire large weird group. So right here, I'm going to immediately go for the root test simply because of this overall n power on the series there. Okay, so I'm going to have the limit as n goes to infinity of the nth root of sine of n over n to the nth power. The nth root and the n power are going to reduce, leaving me with the limit as n goes to infinity of just sine of n over n, like so. Okay, now we've seen that limit before. Let's talk about it again. Sine is a value trapped between 1 and -1. Okay? Also, we were doing the absolute values here, right? So technically it's going to be trapped between 0 and 1 for what we're doing here. I should go ahead and leave the absolute value on the sign in there just for safety. Okay? But this is going to go to 0. Because the n is going to blow up in size and the sign is trapped an upward boundary of 1. Okay? So this guy converges absolutely. Next, same idea. I see that big old nth power on there, and therefore I want to compare these things with the root test. So I'll take the limit as n goes to infinity of the nth root of the ln of 6n over 6n plus 7 to the n. Okay? Then the powers will wipe, leaving me with the limit as n goes to infinity of ln of 6n over 6n plus 7. Now I have infinity over infinity there, and remember, I can't actually do L'Hopital's rule with n because n is a counter, but I can say that the way this limit is set up, it is equivalent to a limit of a continuous variable x, and I then can do the ln of 6x over 6x plus 7. The derivative of each leaves me with the limit as x goes to infinity of 1 over 6x times 1 over 6. The 1 over 6 comes from here, and then the derivative of the ln 6x, whoops, I meant to do this, it's 6 over 6x. The derivative of the ln of 6x is 1 over x. And then the 1 over 6 comes from his denominator. That's that part of L'Hopital's rule. But x is going to infinity, so we're getting 0 for this limit here. Therefore, this converges also. Absolutely. Okay? So it's deceiving on some of these, right? You're raising something to a power that's increasing without boundary. The exponent is increasing without boundary. So that says something for the size of what's going on inside is decreasing fast enough that that power can't overtake and make it explode to being unbounded itself. Okay, what if I have combinations like this? I can see the n to the n. Something like that really should only be handled with a root test, right? Let's go ahead and do that. I'm going to take the limit as n goes to infinity of the nth root 5n plus 4 over the nth root of n to the n. And of course, that's going to leave me with the limit as n goes to infinity of, now the denominator is obvious because the power and the root are opposites. So it leaves me with the n after these two wipe out. That numerator right there is a little bit more obscure and is a limit that we didn't write down earlier. But just think about it, it should make sense to you. The limit as n goes to infinity of the nth root of some number to the power n. See, if it were just like this, the n power and the n root would wipe out, just like they did, in things like this right here, leaving me with the 3 squared. So adding in some other constant like this is not going to change anything once n gets to infinity, or really close to being in the unbounded region, right? C to a very large number is going to be ginormous. If I add a number, you're not really adding much to it. And then as the nth root gets more powerful and chopping it up too, it's going to end up being the same value as it would be without that constant. Okay, it's still going to be C. So in this case, it's like I have the nth root of 5 to the n here. It's just going to be 5 in that numerator. And then the limit as n goes to infinity of 5 over n is 0. So this one also converges. Absolutely. Okay, so as I was saying before, you can see that the root test is a very powerful tool, especially when you want to handle some of these weird setups with n powers or things that have factorials in them. The ratio test handles them just as well, but the root test can be useful in many applications as well. Okay, so I hope this lecture has helped you see how ratio and root tests fit in with the rest of the test and sort of finish out that variety. You should be able to find convergence and divergence of pretty much any series that's thrown at you, basic series that's thrown at you. Now it's time, after you've practiced this skill and made sure you got all of the series tests, it is now time for us to upgrade. The next lecture, be on the lookout for us starting to study back with functions again, and we'll start talking about something called power series as we get deeper into this unit.